Great. Hello, everyone. Welcome to Physics Teacher. In this live broadcast, I am going over a bunch of questions from the Electrochemistry unit for grade 12 chemistry that might appear on a test. So let's get started because I got a bunch of multiple choice questions to get us started. If you have any questions along the way, just let me know in the chat. All right, so our first question says an oxidizing agent can be described as a substance that loses electrons. Well, no, an oxidizing agent is reduced. An oxidizing agent is reduced. And if you're reduced, you gain electrons. So let's just get rid of these two options right away. And that last one, which is ridiculous. So we're already left with two options now. So, I've already said it's reduced and it causes oxidation. So it's not oxidized, it's reduced. So nope. So we are left with C. Process of elimination works for us. Okay. Any questions with that one? All right, let's try the next one. So my students need to know what a down cell is. Basically, a down cell is made with molten sodium chloride. It's not an aqueous solution in water. Okay. So what's produced at the anode? It's made of molten sodium chloride. That's not produced at the anode. It contains no water. So it's really a 50-50 here because we have an anode and a cathode. And at the anode, we get chlorine gas. Okay, sodium metal is produced at the cathode. All right. Let's move on. Next one. All right, true or false? The following reaction is spontaneous. Okay. This is just a true or false question, but this is going to take a little bit more analysis. First, we need to know what's the reducing agent and what's the oxidizing agent. So let's look at sodium. Sodium initially has a charge of 0, and over here it has a charge of +1. So those are the oxidation numbers for sodium. So what happened? Did it lose or gain electrons? In this case, it lost electrons. I know that sounds backwards because we're going up to +1. Remember, electrons are a negative charge. So if you gain electrons, you become more negative, not more positive. So in this case, we are losing 1 electron. And if you lose an electron, you're oxidized. So that means you are the reducing agent, which would mean bromine is the oxidizing agent. But if you want to just double check that, you can. So here we have a charge of 0 to a charge of -1, gaining electrons. So we gain 1 electron. If it's gaining electrons, that means it's reduced. So this is our oxidizing agent. Now, to determine whether or not the reaction is spontaneous, you need to look at a chart of the relative strengths of reducing and oxidizing agents. You can probably find one online. I'll show you one in a minute. But if your oxidizing agent is above your reducing agent on your chart for relative strengths, then it is spontaneous. So let's look up these ones. So let's close this. And here we go. So this is the one I give my students. So we need to first find our oxidizing agents. So oxidizing agents are over here. Need to be able to select that layer so I can write on it there. So there's our oxidizing agents. And we need to look for bromine. Right there. So bromine is an oxidizing agent. So there's our oxidizing agent. And our reducing agent was sodium. So if we look for sodium, it's all the way down here. So there's our reducing agent. So in this case, yes, the oxidizing agent is way above the reducing agent. So if we go back to our question right here. So yes, need to select it. Yes, it is spontaneous. So true. That one is going to be true. Any questions so far? I don't see any in the chat, so we will move on. Another multiple choice question. Electrolysis may be defined as generating electricity with the use of spontaneous reactions. No, a galvanic cell uses spontaneous reactions. An electrolytic cell uses electricity to force non-spontaneous reactions. So you can just get rid of that. So that's not an option. B, generating okay, yeah. Without the, no, you need electricity. No, no, you need electricity to do it. Generating non-spontaneous reactions with the use of electricity. Yes, that's the one we're looking for. What are D and E? Nuclear reactions, biologic? No, those ones are ridiculous answers. Okay, so our answer is going to be C. You probably couldn't see D. Sorry, let me scroll down. That was E. But don't worry, it's not biological reactions. Any questions? Okay, so there's some examples of multiple choice questions. Let's go over how to balance. I get a lot of students constantly asking me how to balance. Let me scroll so we can see the whole reaction there. Move this over a bit. There we go. A lot of students asking me how to balance. I actually created a tutorial last week that I posted on YouTube where I go much into depth on how to balance. I show acids, I show bases. We go over it completely. And then I also show a different method how to do it. So here I'm going to do the oxidation method. I think that's the popular method. But I also show you how to balance a reaction using half reactions, which is very useful. And I actually find it easier in a lot of situations. But let's do it this way. So this is a base. So we're going to balance this base. So we're going to start by finding all of our oxidation numbers. Okay, so oxygen has -2. And we have 4 of them. So that's a total of -8. Now the whole molecule has a charge of -1. So we need one more negative charge than positive. So therefore, if this is -8 in total, and we need one more negative charge, then manganese will be +7. Okay. Moving on, let's see what happened to manganese over in our products. We have oxygen, which is -2, and we have 2 of them, so that's a total of -4. It's a neutral molecule, so manganese must be +4. So what happened to manganese? It went from +7 to +4. So in this case, manganese gained 3 electrons. So we gained 3 electrons. Okay. Next, what happened to carbon? So nitrogen is -3. And our overall cyanide molecule is -1. So we need one less positive charge. So carbon is going to be +2. Nitrogen hasn't changed its oxidation number, neither has oxygen. So it's really carbon that we're interested in. What happened to carbon? Well, we've got oxygen, which is -2. We have nitrogen, which is -3. So that gives us a total of -5, but the overall molecule has a charge of -1. So we need one less positive charge. So carbon is going to be +4. So in this case, it has gone from 2 up to 4. So it has lost 2 electrons. Now, a good thing to do, I don't really see this in this case, but it's to also balance your elements that are not oxygen or hydrogen, right? So you can check manganese. We have 1 here in our reactants, 1 here in our products. Carbon, 1 and 1. So in this case, everything is already good. What we need to do is balance electron transfer. We can't gain 3 and lose 2. That's not conserving charge here. Right? So we need to find the lowest common multiple, which turns out to be 6. So to get 6, I need to multiply these by 2 and multiply these by 3. So I'm going to write that in the equations. So I'm going to put a 2 here and a 2 here. And I'll put a 3 here and a 3 here. Okay? So that's the first big step. If you get that far, you're doing really well. Next step is to balance oxygen. So here we have 4 oxygens, none over here. So in total, in our reactants, we have 4. And in our products, here we have 2. And over here, we have 1. So a total of 3 over there. So I need 1 more oxygen in our product. To balance that, what I'm going to do in our products is I'm going to add water molecules. So I'm going to add 1 water molecule. Okay, that leads to another additional problem. These are so much fun. Hydrogen is not balanced. Now we don't have hydrogen anywhere in this reaction except for in that water molecule we just created. So to balance it, what I'm going to do is in our reactants, I am going to add 2 hydrogen ions, aqueous, and this is liquid. All right, I added 2 hydrogen ions, but this is not an acid, it's a base, so I need to fix that. So what I'm going to do now is I'm going to add hydroxide ions, the same as hydrogen, but to both sides. So I'm going to add 2 hydroxide to the reactants, and I'm going to add 2 hydroxides, aqueous, to the products as well. Now these ones will combine to form 2 water molecules. And then we can simplify the water molecules. And I have 2 over here, 1 over here, so I can cancel one of these with one of those. And now your action is balanced. It looks kind of messy. I understand that. But what we have is we have water plus these reactants. And that gives us these products plus our 2 hydroxide ions. So that is a balanced redox reaction. Is there any questions with that one? No? Okay. All right, galvanic cells. Now this is a question I told my students they will definitely have, so prepare for that. They are going to have to draw that galvanic cell, write the half reactions for reduction and oxidation, write the overall reaction, and then determine the electric potential of the cell. That's a lot. Let's do that one step at a time. You're going to see my artwork today. Nothing in the comments about how bad it is, okay? I already know that, so it wouldn't be any additional information. So here's our cell. I'm going to create just a porous barrier in the middle. So that's just our barrier. Okay. And I'm going to have this as aqueous. And on one side, we have our cadmium. So that is CD, solid. And on the other side, we have our silver. So Ag, solid. Now, the notation is this is our anode, and this is our cathode. Right? So our anode is over here, and our cathode is over here. So without any power source, because that becomes an electrolytic cell, without any power source, the electrons are going to go from the anode to the cathode. So here's our direction for electron flow. Okay, and in our solutions we have, of course, ions. So we have cadmium ions plus 2 and silver plus 1. All right, so what's being reduced? what's being oxidized. Let's first check out our reduced. Okay, you reduce if you gain electrons, and the electrons are going over to silver. So silver is being reduced. So let's write that. So we've got silver ions gaining these electrons, forming our silver solid. Should write the states here, AQ. Okay, so our oxidized then is what's losing our electrons. That's our cadmium. So we have CD solid, losing electrons, becoming our ions, 2+. Now it's 2+, so it has to lose 2 electrons. All right, so before we write our overall reaction, essentially we just add the 2, but it's not going to work. We want the electrons to cancel. Notice here we are gaining 1 electron but losing 2 electrons. So what I'm going to do is I'm going to multiply this whole reaction by 2. So I'm going to write a 2 here, a 2 here, and a 2 here. So now when I add them together, these didn't change my color there. These 2 will cancel. So our overall reaction, we just add them. So we have 2 Ag plus aqueous plus, and we got CD solid, gives us in our products, we have 2 Ag solid and our aqueous ion. So there's our overall reaction. All right, now the mathematics. The last part of the problem, we need to figure out what the potential is for the cell. So to do that, which color have I now used? Green. Okay. To do that, our equation is the potential, standard potential for the cell is the potential for what's being reduced minus the potential for what's being oxidized. All right, so how are we going to figure that out? We're going to go back to our strengths, because notice at the side, they tell us the potential. Oh, I need to write it right there, potential. Okay, so first, what's reduced? So let's look for that one right there. Silver, 0.8 volts positive. Remember that number in case I forget. Let's look for what's oxidized. Here we go. Right there. And negative 0.4 volts. So we're going to use those values. Let's go back to layer 2. So what was reduced? We had 0.80 volts minus, we have a double negative, so be careful with that, negative 0.40 volts, which gives us a total of a 1.2 volt battery. Questions? Comments on my wonderful artwork? No? It's all right, I get it. Okay. There's no questions, so we're like whizzing through this. So I got one more that we are going to do. And this is sort of a stoichiometry question, but it will contain a little twist here. Let's go to black. So here we have a trophy company setting up a nickel plating cell using an electrolyte containing nickel 2 ions. Predict the current required to produce nickel metal at the rate of 5 grams per minute. All right, so we've got nickel 2 ions. So that's like this, AQ. And to produce nickel, we are going to need to add 2 electrons to that. And then we will get our nickel. So that's our half reaction there. All right, let's write what we know. So this part is what's tricky here. 5 grams per minute. That's not telling us one piece of information. That's telling us 2 pieces of information. The first is that we are getting 5 grams of nickel in a time of 1 minute or 60 seconds. Okay, so that's giving us two pieces of information. Now, the equation we use with the electrons is if you want to know the number of moles of electrons, it is current times time divided by Faraday's constant. Now we know Faraday's constant. Faraday's constant is, I shall write it somewhere where you can see over here. All right, not much room. But Faraday's constant is 9.65 times 10 to the 4, moles, coulombs per mole. Okay, but we don't know current, so I can't figure out the number of moles there. But current is what I'm searching for. So if I simply knew the number of moles of electrons, tried to change my color, it didn't work. If I simply knew the number of moles of electrons, then I can use this equation to find current, because I know time and I know Faraday's constant. Okay, well, how can I figure out the number of moles of electrons without using this equation? Well, I know how many grams of nickel you have. So if you look up the molar mass of nickel, it's 58.69 grams per mole. Okay, just use some grade 11 chemistry here. And we can figure out the number of moles of nickel. So moles is mass times molar mass. Mass divided by molar mass. So we get 5 grams divided by 58.69 grams per mole, which gives us 0.0852 moles. All right, now here's where the stoichiometry comes in, because this is a 1:2 ratio. So 1:2 ratio is going to equal the number of moles of nickel, 0.0852 moles, over the number of moles of the electrons that we want. So just doing a little bit of cross multiplication, we can figure out the number of moles of electrons just by taking 2 times 0.0852 moles. And we get 170 moles of electrons. So now we have number of moles of electrons. So going back up here, let's rearrange this equation. For rearranging to solve for current, current is going to equal multiplied by Faraday's constant. So we have the moles of electron times Faraday's constant and divide by time. So the moles we have right here, Faraday's constant is up here, and time is right there. I don't have much room, but you could substitute all those values into your equation to get a current of 274 amps. So that's how you do that kind of stoichiometry question. Okay. If you need any more help, again, go check out my balancing tutorial. And I did another tutorial which is all on electrochemistry, which has more practice problems than electrochemistry. You can look at that. And for my students that have their test tomorrow, good luck. Does anyone have any last questions before I say goodnight? Can I scroll down? Oh, sorry, you didn't see me write that last part. Sorry about that. Any other questions? You're welcome. All right then, if there's no more questions, good night everyone, and if you have tests coming up, good luck.